Okay, good morning already. It's 12:10, March 11. Good evening, the entire world. I am Professor David J. De Los Reyes. My topic for tonight will be lesson number 18 on my long-form video, Advanced Mathematics, and the topic is actually Laplace transform formula number 4. The last time around, I finished Laplace transform number 1, number 2, and number 3. I give you the formulas, then I try to derive it. So later on, when we will use it, okay, it will not come out of our minds. So because if we know our so-called derivation, much more that we will retain the formula in our mind. Okay, let's proceed for this morning. I will check my camera. My lesson for this morning, it's March 11 here in Los Angeles, around 12:11. Okay. My topic will now be Advanced Mathematics lesson. This is now number 18. Okay. And we are discussing Laplace transform. So for tonight, I will be bringing out formula number 4. Okay, then I will try to derive it so we could retain more importantly in our mind when we will be algebraically manipulating a problem under Laplace transform. Okay, the fourth formula is actually this. This is formula number 4. The last time around, we finished formula number 1, formula number 2, and formula number 3. Okay, I will repeat first the first 3. The Laplace transform of 1 is 1 over s. And the Laplace transform of b sub 0 is actually b sub 0 over s. B sub 0 is actually the initial voltage at time t equal to 0. We are referring here to circuit analysis, okay? And the Laplace transform of e raised to at is actually 1 over s minus a. Okay? This is an exponential function, and the formula under Laplace is actually 1 over s minus a. Okay, let's proceed with number 4. For number 4, it is much more complicated because this will now be applied to solution of problems under circuit analysis under AC circuit, the one we have finished. Okay, formula number 4 will be this: the Laplace transform of cosine of omega t. Cosine of omega t. Omega is the natural frequency of oscillation. Natural frequency of oscillation. And under circuit analysis, this is actually 2 pi m. So if we see omega over here on Laplace transform, it refers to the natural frequency of oscillation, and this is 2 pi times the frequency of the alternating current source. The Laplace transform, I will repeat it, the cosine of omega t is actually s over s squared plus omega squared. So when we are solving problem for a differential equation using differential equation, this will be the equivalent of only any cosine function. That will be s squared over plus omega squared. Okay, let's try to bring out the derivation. The derivation of this, we will be using Euler's equation. I think I have not discussed this one, but on the on the next topics of the advanced mathematics, I will be discussing this one. But for tonight, I will just give you the equivalent of Euler's equation. Euler's equation. He is one also of the so-called inventors of advanced mathematics. He formulated an exponential equivalent of the function. Okay, for Euler's equation, e raised to plus j omega t under him is cosine of omega t plus j sine of omega t. real part, this is the imaginary part. Meaning, a raised to plus j omega t will be cosine of omega t plus j sine of omega t. And e raised to negative j omega t, negative. The first one is plus. This should be cosine of omega t minus j sine of omega t. Meaning, if this is minus, this should be minus. If this is plus, this should be plus. So this plus here, okay, this plus here emanates from this. And this minus here emanates from this. So under Euler's equation, I will repeat it again. A raised to j omega t will be cosine plus j sine of omega t. A raised to negative j omega t will be equal to cosine of omega t minus j sine of omega t. What will be the reason why we bring out this one? Because we would like to bring out the equivalent of cosine in terms of an exponential function. Okay, you know now the reason? We use Euler's equation to bring out the equivalent of cosine in terms of exponential function. Okay, I will try to check my camera again. Oh, it's still fine? Okay. We add equation number 1. We call this equation number 1. And we call this equation number 2. Then we try to add these two. We add equations number 1 and number 2. So the operation here is actually plus. So for the left hand side, a raised to plus j omega t plus e raised to minus j omega t is this one. Okay? And for the right hand side, the operation is additions, right? This is j sine of omega t, this is minus j sine of omega t. So actually, if we try to perform the additions of the operation addition, this will cancel out. So what will just remain on the right hand side will be this cosine, this cosine, this is 1, this 1. So this will be twice cosine of omega t plus 0. This is because the sum of this is 0. Or this is gone. And if we try to compute for cosine of omega t, we rearrange. Okay, we divide all the terms by 2, so it will just be simply cosine of omega t. For the left hand side, we divide it by 2, so that will now be 1/2 times the quantity a raised to j omega t plus a raised to minus j omega t. Okay? So we will now try to bring out the formula how to take the Laplace transform. The Laplace transform of cosine of omega t. We didn't do the Laplace immediately. We took first the equivalent of cosine of omega t in terms of an exponential function. So the Laplace transform of cosine of omega t, this is a symbol for Laplace, big letter L, equal to the integral from 0 to infinity. The resulting, this is actually function of t. Okay, this whole term here. So we will substitute the computed cosine in terms of exponential, and we term that as function of small letter t. It is this, right? We add the dt, okay? And under Laplace, to take the Laplace transform, it will be the integral from 0 to infinity of function of t dt times e raised to minus st. Okay, we add this one. That is a standard formula for taking the Laplace transform of any function of t dt. Okay, proceeding with the integration. This 1/2 is a common factor, we bring it out. So they should be 1/2. The integral from 0 to infinity, okay, e raised to j omega t minus st plus e raised to minus j omega t minus st, close quantity dt. We now apply the laws of exponent here. Same base, different exponents. So if we try to expand the right hand side, the exponent of the first one, it is the sum of the exponent, right? J omega t minus st. Second one, it will be minus j omega t minus st. Laws of exponent. same base, different exponent, so it will be same base, then the sum of the exponent. Okay, so this will be equal to the integral, or 1 half the integral. We simplify the exponent. We just compress the value g omega minus s close quantity t, because t is a common factor. Second one, it will be minus g omega minus s close quantity times t, a common factor also. And if we try to integrate the first one and the second one, they should fall under the so-called integration of exponential function, but we must have to bring out the verification. For the first one, the value of the exponent is g omega minus s times dt. Omega is constant, s is constant, so if we try to take the differential of this, du will be this constant here times the differential of time. So du will be g omega minus s, they are constant, times the differential of t, which is dt. So this is not exact. Why not exact? We don't have this term here on the first one. So we must add this one here in here. No, on this one. Times dt. For it to be exact. For the second one, the exponent of e is actually negative g omega minus s close quantity times time. Okay? du will be minus g omega minus s close quantity. The differential of t will be dt. And this is not again exact, not exact, because we lack this term here. So what we'll do, we'll add this one over here, plus dt, meaning e raised to minus g omega minus s times t times this complete differential as per verification, for it to be under the integral of e to the du. Okay? And for both number 1 and number 2 to be exact, we take the reciprocal of this, and we take the reciprocal of this. For the first one, it will be the reciprocal of g omega minus s as actually 1 over g omega minus s. And this now falls under exact e to the du, and it will be e raised to g omega minus s close quantity t. The second one, for it to be exact, we take the reciprocal of minus g omega minus s. So this is 1 over minus g omega minus s. Okay? After placing this one outside, it now falls under the integral of e to the du. So this will be times e raised to minus g omega minus s close quantity times time, close bracket, with the limit from 0 to infinity. Okay, so this is now just a matter of applying the so-called limits. If we try to consider first the first one, just this one. Forget this one for the meantime. If we apply time t for the first one, okay, it will become a raised to negative infinity. Okay, and this will be 1 over infinity, and 1 over infinity will be 0. So for the first one, if we apply the limit to the infinity, the value will be 0. Okay, minus the value of the lower limit. So this is minus. When time t is 0, this will become a to the 0. And a to the 0 is 1. So when we apply the lower limit for the first one, the value of the second one will just be simply minus 1. Okay? Then consider again the second one. Forget this one. Consider this one. Apply the upper, lower, and upper limit. When time t will be infinity, the first one will be 0 again. Same as the first one. This 0. And when time t is 0, e to the 0 will be 1, so this is minus 1. Close bracket. Okay? So the meaning of this, the first one, this is the value of the upper limit, lower limit. Second one, this is the value of the upper limit, lower limit. Simplifying this one, this should be 1 half. Okay? This is minus. We bring this minus down. So what will come out for the first one will be 1 over minus s times minus 1 will be now be s, and my g omega times minus 1 will be minus g omega. I write the s as the first one because it is now plus, because minus s times minus 1 will be plus s. So the first one, if we try to simplify this one, it will be 1 over s minus j omega. For the second one, if we try to multiply all the terms by, or the denominator by negative 1, this will be both positive. So this is plus 1 over minus j omega times minus 1 will be plus j omega, minus s times minus 1 will be plus s. So if we try to simplify the second one, okay, after eliminating this minus 1 on the numerator, we put it in the denominator. What will come out will just be simply 1 over s plus j omega, close bracket. I'll check my camera. Okay, so it is just a pure algebraic manipulation. So this should now be equal to 1/2. I'm following this. This is now addition of, what do you call this? Fraction, two fractions. The one you are viewing under short videos, you're adding two different fractions. So 1 times s plus j omega will be this. We call, Mr. Ben called this the butterfly method. 1 times s plus j omega is s plus j omega, and 1 times s minus j omega, that's why you call this butterfly method, right? This is s minus j omega. And the resulting denominator will be the product of the first one times the second one. So it will be s squared. Actually, the middle term cancels because s plus j omega times the quantity s minus j omega, the middle term cancels. S times s is s squared. Middle term is j omega s, the product of this, plus this minus j omega s, and the last part will be j, and j will be minus j squared, and omega times omega is actually omega squared. So actually this cancels. So what comes out is s squared minus g squared omega squared. Okay? But we will replace g squared by the value -1. So the simplification will just be simply 1/2. S plus s will be 2s. S squared, the middle term cancels, right? So what remains on the denominator will be negative open quantity. The value of g squared is actually -1 times omega squared. So the final formula on how to take the Laplace transform of any cosine of omega t is equal to these two here cancel with this. Right? So what remains on the numerator will be s, and for the bottom portion it will be s squared. This is minus minus, it will now be plus omega squared. So as formula number 4 for transforming any cosine of omega t to Laplace transform, the equivalent will be s all over s squared plus omega squared. And this is actually formula number 4. And it is this. So memorize this by heart. This will be formula Laplace transformation formula number 4. This is number 1, number 2, number 3, number 4. So the next time around I will discuss number 5. We do it gradually. Okay, so our mind will not be saturated with this. If you think it's complicated, it's not complicated. So I will repeat it for tonight. The Laplace transform of cosine of omega t will be s over s squared plus omega squared. That's formula number 4. Okay, that's it, guys. So for those who are taking up advanced mathematics, formula number 4 will be this. The Laplace transform of cosine of omega t equal to s all over s squared plus omega squared. So if you would like to subscribe to my channel, okay, my channel is at youtube.com/@ProfDavidJ.Reyes, and if you want to share it, please click share. This is for you guys, okay? This is advanced mathematics. The topic is Laplace transform. Okay, good morning from Los Angeles. Thank you.